Nave settoriale gruppo 1. Frazione vapore. 52 alta, 1350. Numero giri soffianti. 250. Preparare canale 10H02.
You are listening to the voices of men at work in a nuclear power station. For the very first time in a room of this kind, orders are being given in Italian. A momentous event in Italy's working history. In the flat land round Foce Verde near Latina, where sheep used to graze and the ruins of ancient fortresses recall the fierce battles of long ago, one fine day in November 1958, a foundation stone was laid. This was the start of what was to become the Latina nuclear power station, the first plant of its kind in Italy and on the continent of Europe. On that occasion, the president of ENI, Enrico Mattei, made this speech.
Questa centrale che sorgerà è la prima dell'Europa occidentale.
This will be the first power station of its kind in Western Europe. Italy, after producing Enrico Fermi, one of the first atomic scientists, marked time. Certainly, compared with other countries like Britain and the United States, which today have thousands of nuclear engineers, technicians and experts in the field, Italy, 2 years ago, had only a few dozen experts. Much lost time has been made up since then, as these few dozen have become several hundred. This is how the Latina nuclear power station was born. Only a few days after the laying of the foundation stone, there was a change in the appearance of the area. The land, taken by assault by bulldozers and excavators, submitted to man's operations. Civil engineering work on a nuclear power station includes the reactor building, which is a tremendous job. The foundations, for instance, must support a weight of about 100,000 tons, and a very special type of concrete has to be used to meet nuclear requirements. It's a job on a gigantic scale, and yet it calls for great attention to detail. Tons of material are arriving on the site, and every day the power station's mighty structure grows. Even the machines are huge, like this crane, which is being rigged up under our eyes. Throughout the construction stage, it will handle the erection of the heavy components. It took 4 months to get ready. It is 48 meters high, 53 wide, and can lift weights of about 300 tons. The men on the job have christened it Goliath. Months from the start of the job, we can already see the outline of the reactor building and of the containment sphere. This is what shows that a nuclear power station is being built. The Latina power plant has a net electrical output of 200 megawatts. Let us see how it works. The reactor core is housed in a spherical vessel. It is a graphite structure with vertical channels to take the fuel, natural uranium rods. Uranium-235 generates heat in the fission process. The heat is carried away by a carbon dioxide stream circulated by special machines called blowers. The carbon dioxide heated in the reactor goes to the boilers, giving up its heat to the water and vaporizing it. It then re-enters the cycle. The steam generated in the boilers drives the turbines coupled to the alternators. This completes the cycle which converts nuclear power into electricity. As the steam leaves the turbines, it is in turn cooled and condensed. Thus, as water, it returns to the boilers to restart the cycle. The power station is near the sea, so that seawater can be used to cool and condense the steam. Not all the parts that go to make up a power station can be built on the spot. At the Massa Works of Nuovo Pignone, an ENI Group company, they are working on the shells of the boilers, which, as we have seen, hold and circulate the high-pressure carbon dioxide. There are 6 of them, and their identification plates carry the following description. Height 24 meters, diameter 5.6 meters, weight 230 tons. We are watching them being made, from calandering the plates to welding the rings, from radiographical checks to pressing the ends and stress relieving the whole shell. It is not an easy job. The boilers have to withstand very high pressures, and so the materials are subjected, during construction, to a great many tests. The boilers at Massa, the sphere to take the core at Latina. Because of its size, it is more than 20 meters in diameter and weighs 1,000 tons, it had to be built on the spot, in an area not far from the reactor building. It consists of steel plates 100 millimeters thick, welded together. Saipem, another ENI Group company, is handling this job along with other erection engineering at the power station. It is tricky and complicated work. First of all, the various parts of the sphere, 4 rings and 2 domes, have to be assembled outside and then put in position inside the biological shield. It is the welder's job to put the sections of the sphere together. They have been trained for this at special courses arranged by the site organization. After it is placed inside the biological shield, the sphere is annealed to eliminate internal stresses caused during welding. It is therefore covered with heat-insulating material, and electrical resistances are installed inside. A huge 3,500 kilowatt heater heats the plates to a temperature of 600 degrees centigrade. Now the water and air tests can start. For the former, 4,000 cubic meters of water are put into the sphere at a pressure of 21.5 atmospheres. The air test is made at a pressure of 14 atmospheres. The vessel with the carbon dioxide duct unions is ready. Meanwhile, at Massa Carrara, the boiler shells are nearly finished. Transporting them to Latina was quite a headache. They were too large and heavy to go by rail. If they had gone by road, it would have meant strengthening bridges and altering certain stretches. It was decided to send them by sea, thus reducing to a minimum the distance to be covered by road. Special trailers were made to take the boilers from the works to the port of Massa, where they will begin their voyage. The first boiler, hermetically sealed and ballasted, is launched. At Anzio, the boiler starts on the last lap of its journey. 15 kilometers by a road which has been specially prepared to take this heavy and cumbersome load. Nearly all the bridges have been reinforced, and some electricity and telephone cables have had to be moved. At the site, the Goliath crane receives the boiler. After shot blasting and painting, it is again handed over to Goliath and hoisted into its final position. The powerful giant does its job smoothly. Like all power plants, a nuclear power station needs large quantities of cooling water for the turbine condensers. This is why it was sited near the sea, so as to have available the 20 cubic meters of water per second needed for condensing the steam. So, together with work on the power station proper, the job of building the seawater intake and outlet works was started. On a site near the beach, reinforced concrete tubes are being prepared. They are 3 meters in diameter and 50 centimeters thick. When they have been aligned, they will be connected together by special joints. It is an imposing construction, including the actual water intake, tunnels buried under the seabed, open-air culverts, pumps, filters, and a jetty 700 meters long. A gantry crane mounted on the jetty, one by one, lifts the prefabricated tubes for the seawater intake. It is the diver's job to weld the tubes together, thus forming an underwater tunnel which takes in clean, cold water 700 meters from the shore. The water reaches the filters and pumps through open culverts. On the left we see the intake culvert, and on the right the outlet. From the pump house, which we see being built, the water will reach the power station through underground ducts. Following the route of the seawater ducts, which, as you know, serve to cool the condensers, we find ourselves in the turbine hall. This is where the machinery for generating electricity is housed. The condensers, turbines and alternators are being erected. This large building will hold 3 sets of 70,000 kilowatt turbo alternators and 2 auxiliary sets of 11,000 kilowatts. The latter generate current at variable frequency to operate the 6 carbon dioxide blowers at the different speeds required. At the same time as the machinery, the control panels and cables are being installed. Another small generating plant consisting of 3 diesel sets is nearly ready. It ensures an emergency power supply to such machines as must on no account stop working. Just over 2 years have passed since the job started. The reactor building, control building and turbine house have taken on their final form. The boilers put in place by the tireless Goliath tower majestically. On top of them we see some strange little houses. They are air-conditioned cabins to protect the inside of the boilers while the tube banks are being fitted. The tubes are pickled before being put into the boilers. That is to say, they are given special treatment to remove every trace of rust. From this time on, they must not get damp or dusty. Workmen in blue overalls are replaced by others in white. This means that the nuclear side of work is beginning. Special hermetically sealed cases are used to carry the tube bundles. We go into the air-conditioned cabins. They are essential for fitting the tube bundles into the boilers to ensure a constant ambient atmosphere inside the boilers where humidity is kept to a minimum. These tubes, as we said, will come into direct contact with the carbon dioxide from the reactor. Every precaution must be taken to prevent impurities entering the carbon dioxide circuit. After the vessel and the boilers, which we see in the drawing, the fuel charge-discharge room is another outstanding feature of this reactor. What is a charge-discharge room? It is a large space where, by means of a complicated machine, which we shall deal with later, the fuel is charged and discharged, and all the operations necessary inside a reactor on load are carried out. We have seen that the reactor is housed inside a biological shield of reinforced concrete 3 meters thick. Now they are putting on the pile cap, also in reinforced concrete. It is pierced by 197 standpipes connecting the inside of the reactor with the charge room floor. For some time at the port of Anzio, they have been building the intake works. The large basin through which the water for the power station will pass is ready. It is towed to the end of the jetty where it will be submerged and anchored to the seabed by injecting concrete. Towards the end of the third summer, the civil engineering work is nearly finished. A plant has been built to produce carbon dioxide to the required degree of purity so as to ensure that a cheap supply of the right kind of gas is always available. Alongside the turbine house, the electricity substation structure is going up. For some time now, they have been checking on natural radioactivity within an area of 30 kilometers of the power station, taking samples of plants, earth, and water. At the power station's radiometric laboratory, the samples are subjected to thorough analysis and then burnt. The degree of radioactivity can be ascertained from their ashes. Now it is the turn of the Geiger counters. They measure existing radioactivity before the power station goes into operation. In this way, the minimum future variation can be checked. Inside the reactor building, they are installing the 6 blowers. These are large fans powered by variable speed electric motors which send more than 3,000 kilograms per second of carbon dioxide into the reactor at a pressure of about 14 atmospheres. A kind of hurricane to carry away from the reactor core the tremendous amount of heat generated in the fission reaction. From now on, any delay in the work of one sector would slow down the others. For the ENI group engineers, specialists and workmen, 0 hour is approaching. Theirs is the honor to be the first assigned to a pioneering project in Italy. We approach the pressure vessel. It is a prohibited area. Anyone entering it must comply with strict regulations. He must change into special overalls and leave behind all personal effects. This is a necessary precaution to prevent any foreign bodies getting into the reactor which might adversely affect the fission reaction. Passing through one of the gas ducts, we enter the vessel. They are fitting the insulating panels which will prevent heat losses. Outside the vessel, in a special room, they are preparing the plates on which the graphite rests. After shot blasting, the plates are carried in special containers into the vessel to form the floor on which the core will be erected. Now, for the last time, we can appreciate the size of the vessel. Laying the plates is high precision work, to tenths of a millimeter. The workmen are fitting the gags into the holes in the plates. These are in stainless steel, and the base of the graphite blocks is fitted into them. They enable the gas to flow into each channel. The steel cage from which we are watching the start of the construction will hold the reactor core and keep it perfectly steady. In order to keep a continuous and meticulous check on the temperature of the graphite structure, the radiation level inside the reactor, and the perfect functioning of the fuel elements, delicate apparatus controls thousands of circuits. Thus, the slightest variation is immediately signaled to the control room, and man, while keeping well away from radiation hazards, can take action to correct and change the course of the fission reaction. The Latina power station reactor is graphite moderated. The arrival of the graphite shows that the final stage has been reached. Roughly 2,000 tons of highest purity graphite with a 99.9% carbon content are sent to the magazine. Special linings and air conditioning inside the magazine maintain the graphite's purity, and each block is carefully checked before being put into the reactor. And here it is in the reactor. The workmen are putting it into the cage container. The graphite blocks are fitted one into the other so that the holes through them are perfectly aligned. These holes form the channels into which the fuel elements and control rods are inserted. The reactor operation implies the use of a spent fuel decay pond. As we see from the sketch, the spent uranium rods are conveyed to it by a special machine. The uranium rods are taken without any contact with the outside, straight from the reactor to the pond, and left to decay underwater for 100 days, and then sent to the reprocessing plants. Other plants treat the water in the pond to remove every trace of active substances. The camera's eye has given us a brief view of the construction of the power station. We now know how it was built and how it works. Now we are going to see how its three main components, the reactor building, control room, and turbine hall, are interconnected. We only have to go down into the basement. Thousands of cables, 400 kilometers of them, carry signals, impulses, power. If we follow them, we find ourselves back in the turbine hall. They have nearly finished assembling the turbo alternators and auxiliaries. Outside, the substation has taken on its final form. From here, the lines go out to the places which will use the electricity produced by nuclear fission. It will not be long now. In the charge room, they are installing the control and safety rod motors. Meeting the charge-discharge machine is like meeting some robot out of science fiction. It is 17 meters high and weighs 450 tons. It is the engineer's most faithful friend. At their command, it loads and unloads the uranium rods, drops the spent fuel down into the decay pond, and works where man cannot enter. It is now summer 1962. The final touches are being put to the power station. The offshore work, too, is in the final stages. They are bringing the last lengths of piping onto the jetty. The divers are assembling the last stretch of tunnel. This has been a tough job. Man's skill and perseverance have got the better of the waves' violence which often threaten their work. Intake works, we see them taking down the diaphragm between this and the tunnels. power station's nerve center is the control room. Here the orders are given for operating the plant. Here the signals arrive from all the instruments. The day is approaching when the reactor will be charged with the first uranium rods. An operator is testing the controls of the charge-discharge machine. At last we see it working. Inside it has foolproof devices which enable the fuel to be changed while the reactor is on load. With marvelous precision, this machine will pick out the one channel out of 3,000 which requires attention. They are preparing and checking the supports on which the fuel elements will rest. The dialogue between the charge room and the inside of the vessel is warming up. Orders and OKs alternate with technical jargon. A team of experts has been formed which can now pass the final test. A date has been entered on the work schedule. The date for meeting element U-235. The vessel is ready to take the uranium. They are lowering tube bundles into it to enable samples of carbon dioxide to be taken to check its radiation level. The 100 control and safety rods are in position. They regulate the amount of power generated by the 23,426 uranium rods. Now they are starting to load the fuel. This is the day for which management, engineers and workmen have striven for 4 years. The uranium in its metal cans is on the pile cap. The engineers cannot hide their excitement. They are surely reminded of the men who, 20 years ago, under the direction of Enrico Fermi, loaded the first atomic pile. Then it was an act of faith in science. Today it is a rite carried out according to strict rules. Each fuel element is carefully checked. Each uranium rod entering the reactor brings criticality nearer. The radiation level is measured the whole time. The Geiger counters stand guard over the men's safety. At last, the chain reaction has begun. The reactor has gone critical. The first nuclear test is completed. Work goes on. The crates of uranium are being emptied one by one, and the fuel goes into the core until it is full. The cinema gives us this privilege. The last views of the reactor vessel. In a few moments, the control room will order all out, and the miracle of converting matter into power will be hidden forever from the layman's eyes. But man, although a long way away and shut out by thick cement walls, still has the upper hand. The control room panels signal that matter is liberating energy, generating heat, that the turbines are revolving. Electricity, above all, it can be said that a promise has been kept. A promise given by Enrico Mattei when he laid the foundation stone. Italy, he said, hopes also by means of nuclear energy to reach rapid independence in the field of energy sources. This power station will contribute, therefore, to the formation of the teams and of the experience necessary to carry her forward, towards progress in the nuclear field, towards the future.